Okay, so a function is a situation where you have a rule, a mathematical rule, where it takes each x value and assigns it to exactly one y value. Let's take a look at a couple of examples. Let's say we have some x values and some y values. If x has a value of 1, let's say the y value is 4. If x has a value of 2, let's say it's 9. If x is 3, let's say it's 17. I'm just making these numbers up, okay, just in case you're wondering, where's he getting these? If x is 4, y is 9. Now the question might be, does this represent a function? And you'll see the point of concern here, and I've rigged this, the point of concern here is there are two x values that go to the same y value, aren't there? You see it? X equals 2 has a value of 9. X equals 4 has a value of 9. Okay? For a function, that's legal. Let me compare that to something that's not legal. Let's say we have x and y. Let's say we have x1, 4, x2, 9, 3, 17, 4, 9, 1, 8. The concern is, where does the repeat occur? Okay? This is a function. This is not a function. The difference is, in this first illustration, each x value gets how many y values? 1. So in this first illustration, 1 goes to 4, 2 goes to 9, 3 goes to 17, and 4 goes to 9, but that's okay, because each x value is only given one assignment, isn't it? Okay. In the second scenario, we have 1 goes to 4, 2 goes to 9, 3 goes to 17, 4 goes to 9, and 1 goes to 8. Do you see that 1 is double assigned here? It's kind of like, sorry, my examples are hockey. That's what I live and have lived for years with my son. Let's say we have a situation where you've got, this is your team, and you say, okay, player number 1, you're going to cover number 4 on their team. Player number 2, you're going to cover 9. Player 3, you're going to cover 17. And player 4, you're also going to cover 9. Is it okay to double team somebody? Yeah. Okay. In fact, that's often done, isn't it? If somebody has a really good player, you throw 2 people on them and try and shut them down. Find out just how good they are. Can they play against 2 players? The first example is fine. That is a function. In the second example, you've got player 1. You're going to cover player 4. Oh, yeah, you're also going to cover player 8. How would you like that assignment? That doesn't sound so good, does it? Especially if they go and they're 200 feet apart from one another. How are you supposed to cover both of them? The second example is a situation where you ask one player to go 2 directions. That doesn't work. That hurts. Okay, you can't split in half. So the first one, where you have several x values assigned to the y value, that's fine. If, however, as in the second case, you have one x value assigned in 2 directions, that won't work. Okay? What do these look like as far as a graph goes? Well, in the first case, and I'm just making up something here, okay? So if you're wondering where do you get that graph, I'm making something up. Let's say we have something like this. In this scenario, for a particular y value, it can hit several times, can't it? Do you see that? Different x values can wind up being assigned to that same y value. That's double or triple teaming that y value, isn't it? That's fine. Does that make sense? what you really don't want to have happening with your team is something like this. Kind of fun having all the colors to choose from. Let's say we have something like this. Now, in this situation, it's a little different from the previous one. Different in that for a specific x value here, it's got to do this y value, this y value, this y value. And now you've got one x value trying to go several directions, don't you? That doesn't work. This second graph is not a function. If you are given a graph and asked, does this graph represent a function, there's a very easy way to check to see if it's a function or not a function. Remember, you cannot have one x value assigned to multiple y values. If you can draw a vertical line through and the line intersects that graph more than one time, that means at that x value, because if it's vertical, it's picking a particular x value, isn't it? If that vertical line intersects the graph more than once, that means that x value has to cover multiple y players, doesn't it? Okay? So, to the far right, you can see the vertical line intersects the graph multiple times. When it does that, it is not a function. In the first case, you can draw vertical lines anywhere you want, which means that each of your team players, the x players, is covering how many of the other team? Just one. Does that make sense? This process of looking at, does the vertical line intersect one time, and it's a function, or does it intersect multiple times and it's not a function, is called the vertical line test. And you may well have seen this before. So a quick way to check to see if something is a function or not is to look at the graph and ask yourself, does a vertical line intersect more than once? If it does, you're done. It does not have to intersect more than once in a bunch of places. Let's take something like this. My son and I enjoy the roller coasters at Kings Island. Somebody told me once they have rides other than roller coasters at Kings Island. I never really noticed that. Okay, let's think about something like the vortex for a minute. It's kind of slow, it's kind of boring, but it's okay. Does that graph represent a function or not a function? Well, the thing that might be slowing you down is at some spots over here, it only intersects the graph once, doesn't it? So that qualifies as a function. And look at all these places over here. That qualifies as a function. In this center area, it intersects multiple times. As soon as that happens once, it's not a function. Okay, it isn't part function and part not function. As soon as you get one situation where a vertical line intersects more than once, game's over, it's not a function. Does that make sense to everybody? Okay. All right. With functions, so Chuck's getting a little bit more careful here with his language, like saying with German Shepherds. Now I can't talk about characteristics of Chihuahuas, Poodles, Golden Retrievers, and any of them, do I? I have to specifically talk about German Shepherds. When I say function, it's exactly the same. I can no longer talk about situations where you have loops in them and all kinds of cool stuff like that going on. Okay? I have to limit myself to things that have the characteristic of passing the vertical line test. If we're working with functions, which is what we're going to usually work with, okay, One of the things that we're going to be concerned about is the domain of the function. How do you figure out the domain of a function? This is really, really important. What this really is asking is, what numbers can we use? That's important in a lot of things in life. Okay? One of the things they work on kids early with when they're learning to play hockey is, how are you allowed to hit legal? Can you hit from behind? Never. You hit from behind and you're thrown out of the game. How about, can I go like this and get him in the shoulder? All day long. Have fun. How about if I accidentally go a little higher and catch him in the head? You're toast, baby. Okay? There is no hitting in the head. So you got to learn what's legal, what isn't legal, don't you? And for each function, you got to learn what's a legal play and what's not a legal play for that function. So for example, if we have a function, something like y equals the square root of x minus 5, and you may say, well, Chuck, how do you know that's a function anyway? Well, you could whip out your calculator and graph this thing quick like. And if we were to graph it, it would go something like that. Okay? Don't worry about how'd you get that right now. We'll deal with that later. Not later today, but later. Okay, so look at that function. Does it pass the vertical line test? Yep, so it really is okay to call it a function. So we're good. Now the question is, what's a legal play with this function? Could we use x equals 3 for that function? Is that a legal play? We'll try it. If you replace x with 3, what do you get? -2, don't you? Is the square root of -2 legal in the real numbers? No. In fact, what kind of number is that? It's an imaginary number. Do you ever wonder where they really use those things anyway? Well, they use them in their imagination, Chuck. Okay? It may be in areas that you won't bump into, but it's in things like electronics and fluid flow. Fluid flow. Where is that ever important? Has there ever been anything in your life that was affected by fluid flow? Have you ever used the brakes on your car? Once or twice. I prefer the accelerator though, thanks. How do your brakes work? Great. How do yours work, John? What winds up happening is there's a piston that pushes on some fluid. And that fluid pushes down to your brakes, which pushes out a piston and stops your car. Real quick, there's a lot more to it than that, but we don't really need to be spending all our time on the way brakes work. It's all about fluid flow. There are lots of things that depend on fluid flow around you. You just haven't really given them much thought or had them point out. Somebody's already thought it out for you. But there are a lot of situations with fluid flow, with electronics. Have you ever used anything that has electric? Okay, it's not atypical to have some complex values in with the design on those as well. So they are useful. It's just that you're probably not going to need them too often. Okay, so what we need to do here for this particular function, we know it's a function, is to figure out what are legal numbers to put in, what are illegal numbers, where are we allowed to hit. Okay. In hockey, if the guy's up against the glass, are you allowed to plow into him? Depends how. Okay. Wow, strange. I didn't realize there were that many rules to the game. But actually, even though it looks chaotic, there are actually rules to it. Okay. Here, what are the x values we're allowed to use? And what are the ones we're not allowed to use? What are we not allowed to do? What's going to cause a penalty? Well, we know 3 isn't going to work. Would 0 work? No, because 0 minus 5, square root -5. What's the smallest x value that's going to work here? 5. Got it. Because you can take the square root of 0, can't you? Okay, So the numbers we're allowed to use here start at 0. And can we actually use 0? Ooh, that's a tricky question. Some are going like this, some are going like this, which means overall it's kind of like that. Okay? I'm not sure as far as the class goes. You can take the square root of 0 because what times itself equals 0? 0 times 0. Oh, so you can do the square root of 0. That's legal. All right. So the domain is going to be the set of x such that, let's see, we can start at x equals 5. Can we use 6? 7? Can we use 11.3? Yeah. Can we use 17 over 2? Yeah. Can we use the square root of 122? That's a little bit bigger than 11. Yeah, that'll work. So there's all kinds of numbers that we can use, aren't there? The set of x such that x is greater than or equal to 5 and x is an element of the real numbers. There's one way to write it. There are several different ways to write this. Another way to write the domain is to draw a picture of it. So way number 1 is like this, set notation. We could also draw a number line, and if here is 0, we'd come over to 5. We're going to start there, and we're going to go bigger than 5. Are we allowed to include 5? Yes. So do we fill in that dot or leave it open? You fill it in. If you're allowed to go there, you fill it in. So we could do something like this. Now, I intentionally did this method second because the third way that you can do this is fairly easy to do once you've got the number line. You could write this as 5 is less than or equal to x is less than or not equal to, but just less than infinity. Do you see how the 5 less than or equal to x less than infinity comes right off of the number line? Does that make sense? Another way to write this, geez, Chuck, how many ways are there? Well, we're running out here. We could go from 5 to infinity. Can you ever get to infinity? No. One of my favorite lines is from Toy Story, where he's getting ready to jump off, and what's he scream before he jumps to show he can fly? To infinity and beyond. Can you really get beyond infinity? No, but he's a toy, so you know. Maybe a little hard to explain, but to explain or to show that you really can't get there, you use not a bracket, but you use a parentheses. Okay? So Buzz Lightyear to the rescue. These 4 different methods are all fine for reporting a domain. Which one do you need to use? Well, kind of depends on the situation. How formal do you want to be? Okay. These 2 are most frequently used. This one is a formal method, and if you're looking for a picture, obviously, this one's nice. Suppose we have something like this. So let's do example 2. Let's say we have something like x minus 4 times x plus 3 is less than or equal to, well, we'll do it first less than or equal to 0. Then we're going to turn around and we're going to make it greater than or equal to 0. How would you compute the domain there? First off, does it make sense where the x minus 4 times x plus 3 came from? We factored x squared minus x minus 12. If you factor that polynomial, you get these 2 monomials, and now we got to figure out, oh my gosh, where's this? An easy way to solve something like this is to draw a number line. What are the 2 roots or solutions for this particular inequality? What are the x values that make this equal 0? take a look at the first part, x minus 4. What could you plug in for x to make that 0? 4. So one of the answers, or roots, is 4. Then moving to the second monomial, the x plus 3, what x value would you plug in there to get that to 0? Negative 3, right? So we've got negative 3 and 4. Each of these will make the value 0. Are we allowed to include 0 this time? Yes. So what I'm going to do before I go any further is I'm going to draw dots, color them in. Now, we are only shopping for numbers that will make this negative, aren't we? Well, let's just try some things on for size. Have you ever gone in a store, grab a bunch of stuff, put it in a cart, take it back into the room where you can try stuff on? Yep, this fits. Nope, this doesn't fit. Yep, this fits. Nope, this doesn't fit. And you go through and you just kind of sort things out. Okay, that's what we're going to do here. We'll first pick a number from over in that region. What's a number that's smaller than negative 3? Well, I'm afraid to say, Chuck, I might pick the wrong number. There are an infinite number of choices there. Negative 4 is one of them, negative 5, negative 10. Is negative 52,637,183 a choice? Yeah, why you pick it, I don't know. But it's an option. There are an infinite number of choices there. So let's pick negative 4. There we go. Negative 4. If I plug in negative 4 and negative 4, when you plug negative 4 into the first monomial, what does that work out to be? A positive or a negative value? It's a negative, isn't it? It's a negative 4 minus 4, that's a negative 8. If you plug the negative 4 into the second term, or factor, what's that work out to be? Negative 1. So it's still negative. And a negative times a negative is a... yeah, does this look familiar? Okay, so anything we pick over there is going to be positive. Do not assume that it alternates. It's really easy for me to come up with stuff where it doesn't alternate. So don't say, oh, that's positive, so it's going to go positive, negative, positive. A lot of times it does, but not always. Okay, so be careful. Don't fall into that trap. What's an easy number to work with out of this middle region? I do mean easy. What's the easiest number to work with in that middle region? 1? Think even easier than 1. 0. So I'm going to pick 0 here. Is 1 a bad choice? No. 1 would work perfectly fine. But if I plug in a 0 in each of these, the first factor is going to be 0 minus 4, which is negative. The second factor is going to be 0 plus 3, which is positive. Now you're going to have a positive and a negative multiplied together. What do you get there? Oh, wow. So that means everything in this region is negative. And then if we play the same game over here, pick something like 5. If we plug in the 5s, you're going to have a positive and a positive. This is going to be positive. Now, which regions are we shopping for? Are we shopping for things that are positive or things that are negative in this problem? We want negatives, don't we? Oh, that's right. Because we've got less than or equal to 0. And with less than or equal to 0, we are shopping for negatives today. Probably the easiest way to report the answer is to go like this. I want this region right here. Well, that's starting at negative 3 and going to positive 4. Boom, it's done. X is an element of this. And that's all the more there is to it. It's just that easy. Does that make sense? Look familiar? You've probably done something like this. Okay? If you haven't, that's okay. Let's take this exact same deal, since we've already talked through part of it and we don't have to rebuild a whole lot. And this time, we want the regions that are greater, let's say just greater than 0. I've changed it up. It's not greater than or equal to. It's just greater than 0. Now, the reason I went with the same factors is we can copy down our -3. We can copy down our 4. We know that it goes positive, negative, positive. So there's a whole lot of this already done for us, isn't there? Already done in the previous problem. Do you buy that? Be careful. This time, can we include our roots or not include them? Not include it. You're right. How do you know you can't include them? It's not equal to. See it in the sign? It says greater than. It says greater than, but it says nothing about equal to. So instead of dots there, what are we going to put? Open circles at -3 and 4. Now when we go shopping, we're shopping for the positive stuff. Which means that we want this region and this region. That means that we want from -infinity over to -3. And notice I'm using a parentheses. Why not a bracket there? Because you can't use the -3, right? Yeah. And along with that, union with, once again, a parentheses, 4 to infinity. Does that make sense on how to build those? Are you okay? You can do all kinds of mix and match here. We could also write this. Well, here, we could write this one if you wanted to. We could write this as -3 is less than or equal to x less than or equal to 4. Does that make sense? Up there at the top, how we get that particular interval? What interval would you get for this second example? And if you're not sure, start out simple. Just take one little piece. How would you write that with the x's and the less thans and the greater thans and all that stuff? Well, how about something like -infinity is less than x, less than or greater than the -3? Less than -3. Along with that, now we're going to do 4 less than x less than infinity. In place of the union, if you wanted to, you could put or. Does that make sense? Either notation is fine. Either way to report things is fine. Are you okay with that? Okay. Hey, let's go after, let's see here. Let's go after, looking at the clock, the quiz. We'll call it quits there for today. Now, this has us up to page 39. At this point, we've got the material in section 1.3 up through page 39. We've looked at it. And I'll wait till we finish this section to post homework. Is that okay? Because I'm guessing you probably wouldn't spend a bunch of time on it this weekend anyway. So, if you want to look at things, we're up to about page 39. If you don't want to look at things, you don't have to worry about it till Wednesday when we finish section 1.3.